Okay. Good morning, everyone. Okay. First of all, I would like to thank organizer for providing such a nice opportunity. My name is Keisuke Fujii from Kyoto University, and today I want to talk about the quantum speedup in stochastic adiabatic quantum computation. And actually, in this talk, I will provide a strong computer scientific evidence that there is a quantum speedup in the adiabatic quantum computation, even when the Hamiltonian is restricted to the stochastic one. So this is the outline of this talk. So first, I will talk about motivation of considering adiabatic quantum computation with stochastic Hamiltonian. And then, in order to characterize quantum computational power of stochastic adiabatic quantum computation, I will briefly mention about the mapping from the quantum circuit model to the adiabatic quantum computation. And finally, I will mention about the quantum speedup in stochastic adiabatic quantum computation. Okay, let's start with what is stochastic Hamiltonian. So stochastic Hamiltonian is a Hamiltonian whose off-diagonal elements non-positive in a given standard basis, like computational basis. And by this property, the ground state has positive coefficients. And so there is no negative sign problem. So we can apply quantum Monte Carlo method for this class of Hamiltonian. So a prototypical example of stochastic Hamiltonian is transverse Ising model, which is also employed in the D-wave quantum annealing machine. And also both have a model with negative hopping terms and Heisenberg antiferromagnetic and bipartite graph. So all these kind of important models can be addressed by using quantum Monte Carlo method if you are interested in the thermal equilibrium states. But fortunately or unfortunately, adiabatic quantum computation with stochastic Hamiltonian is thought to be relatively easy for classical simulation with classical computer, and there are extensive effort to realize non-stochastic term in order to get quantum speedup. But at the same time, there is no proof that stochastic adiabatic quantum computation can be classically simulatable. So here we have a very simple question. So what is the potential power of adiabatic quantum computation with stochastic Hamiltonian? And also, is there any gap between classically simulated stochastic AQC and actual stochastic adiabatic quantum computation on actual machine? And also, is non-stochastic interaction only the way to quantum speed up, or is there any other pathway to get quantum speed up within stochastic adiabatic quantum computation? So this is the take-home message of this work. So in the existing work, mostly the measurements on the adiabatic quantum computation is done in the standard basis, like computational basis. But if you consider non-standard basis, like X basis or Y basis, then the situation changes drastically, and you can get quantum speed up. And importantly, this kind of non-standard basis measurement would be relatively easy on actual quantum machine if there is a true nice quantum coherence. And more precisely, if we show that if adaptive measurements are allowed on the final state of adiabatic quantum computation, then such a stochastic adiabatic quantum computation is as powerful as universal quantum computation. And even if the measurements are restricted to the non-adaptive measurements, so the measurement is done simultaneously on the final state of adiabatic quantum computation, then even in such a case, we can find a quantum computational speed up. And this implies that classical sampling is impossible under some computational complexity conjecture. And also, stochastic adiabatic quantum computation can solve very important and meaningful problem like factoring by cleverly using quantum classical hybrid approach. Okay, let's move on to the mapping from the quantum circuit model to the adiabatic quantum computation. Actually, this is based on the Feynman's seminal idea in 1980s. Actually, he introduced tensor product of working space system and the clock system. And by using this clock degree of freedom, we can map each step of quantum computation to the orthogonal states, like this. So then we can define the tight binding type Hamiltonian for these orthogonal states. And here we have a hopping term, which is sometimes called the Feynman's propagator Hamiltonian. And this is a final Hamiltonian of adiabatic quantum computation here. And here we have the initial condition to the clock state and the initial Hamiltonian. And the initial Hamiltonian and final Hamiltonian is connected smoothly. And then this is nothing but the tight binding Hamiltonian, so we can find the exact ground state. And actually, the ground state is superposition of the each step of quantum computation. And if you do the measurement on the clock state and you get the final time t, then you can get the output of quantum computation. And this kind of construction is employed in the proof of the universality of general adiabatic quantum computation, which is done by Aharonov et al. And here we are interested in the case where the Hamiltonian is restricted to the stochastic one. So if you impose stochastic conditions, so how corresponding quantum computation changes. So this is the off-diagonal term of the final Hamiltonian. Here we have hopping term. And if we impose this Hamiltonian should be stochastic, then this unitary operator U corresponds to the quantum computation. So if you impose stochastic property, then each element of this unitary operator should be non-negative, so positive or zero. And we can easily find such a kind of unitary operator, so Pauli X operator, CNET operator, or Toffoli gate like this. And we can easily say that elements of unitary operator U are non-negative if and only if U is a unitary version of reversible classical computation. Actually, this kind of construction is have been used to address Hamiltonian complexity of stochastic Hamiltonian. And here we are interested to the computation power of stochastic adiabatic quantum computation. So actually, the computation power of stochastic adiabatic quantum computation can be characterized as a sampling problem from the quantum circuit described here. So the initial state is zero state, or you can also input, you can also insert Adamov operation to the initial state. Then the circuit, the quantum gates, you are allowed to put is the unitary version of classical reversible computation, like Pauli X, CNET, or Toffoli, or something like that. And finally, you can do any measurement on the final state of the adiabatic quantum computation. So this is the quantum computation associated with the stochastic adiabatic quantum computation. Okay, let's move on to the quantum speedup in stochastic adiabatic quantum computation. So from this formulas, we can easily find the quantum speedup. So actually, even with this kind of restricted quantum gates, we can generate a very useful resource for quantum computation. Actually, we can generate the universal resource for measurement-based quantum computation by using these Adamo gate and control not gates or Toffoli gates, which is so-called graph states or hypergraph states. And if you are allowed to do the adaptive measurement on this final state of adiabatic quantum computation, then you can simulate universal quantum computation on the stochastic adiabatic quantum computation. So in this sense, if you are allowed adaptive measurements, stochastic adiabatic quantum computation is as powerful as universal quantum computation. But unfortunately, in this case, the thing which is done by adiabatic quantum computation is just state preparation, state preparation for the measurement-based quantum computation. And quantum computation is driven by the single qubit, sequential single qubit measurements. So you might think this is not relevant for characterizing the computational, potential computational power of stochastic adiabatic quantum computation. So in this sense, we should restrict the measurement to the non-adaptive measurements, so the simultaneous readout on the final state of the adiabatic quantum computation. Still, even if we restrict the measurement to the simultaneous non-adaptive measurements on the final state of adiabatic quantum computation, we can show the quantum speedup on the stochastic adiabatic quantum computation. Actually, we can show that even in such a situation, we can solve factoring problem based on the Shor's algorithm using Kitai's phase estimation. So actually, this circuit is the circuit for solving factoring problem using Kitai's phase estimation. So here we have a control unitary operation for the phase estimation, and this unitary is a kind of unitary reversible classical computation, so-called modular exponentiation. So in this sense, all these parts can be done on the stochastic adiabatic quantum computation. But unfortunately, if you want to extract phase information, you have to do the inverse quantum phase transformation. And this part includes a control phase gate, which cannot be done on the stochastic quantum computation. So in order to avoid this control phase operation or adaptive phase gate, we introduced the new kind of phase estimation based on samplings. Actually, we perform phase estimation in parallel way with many samples. And if you do the X-based measurement on this unsure state, then you can estimate the expectation value of X operator in this parallel phase estimation. And the same thing, exactly the same thing is also done in the Y basis. Then you can get the expectation value of Y operator here. So by using this expectation value of X and Y, you can estimate the phase factor of the phase estimation. And then you can decide whether the case bit of phase factor is 0 or 1 according to this estimated expectation values. So by using this argument recursively, we perform the whole phase estimation with R samples. Then you get the measurement outcome and do the classical processing to estimate the expectation value. You can decide all binary variables of the phase factor by using stochastic adiabatic quantum computation. So in this sense, stochastic adiabatic quantum computation with non-standard basis measurement can solve the factoring problem. So let's summarize this talk. So adiabatic quantum computation with stochastic Hamiltonian is relatively powerful under non-standard basis measurement on the final state of adiabatic quantum computation. And so this implies that not only non-stochastic term, but non-standard measurements employed here are key to gain quantum speedup. And our construction is a prototypical example where quantum classical hybrid algorithms can enhance quantum speedup, avoiding quantum Fourier transformation, which cannot be done on the stochastic adiabatic quantum computation. And Hamiltonian can be made two local stochastic, one by using perturbative approach. However, computation power of transverse Ising model is still open. And the computation power of standard-based measurement is still open. At least in the present framework, it only results in the classical randomized computation. But this argument cannot be generalized for in the general case. And finally, full Fortran theory is still missing, and this topic will be closely related to the talk given in this afternoon, invited talk by the Elizabeth Crossan. So that's all. Thank you for your attention.
Thank you very much. Questions? Anybody? No?
I wasn't going to ask this because I think I just understood it wrong, but since no one else is asking, all of this work you've shown about the quantum Fourier transform and the Shor's algorithm and all that, that looks circuit-based to me. What is the adiabatic component in that?
Actually, there is a nice mapping between the circuit model and adiabatic quantum computation. So, if you have a circuit for some quantum computation, then you can construct a final Hamiltonian, which correspond to the, so if you do the adiabatic quantum computation using this Hamiltonian, then the output exactly corresponds to the circuit model quantum computation.
Okay, thank you.
So the hopping term itself is clearly stochastic, but when we use perturbative gadgets to turn it into a two-local spin Hamiltonian, does it remain stochastic when the gates are also non-negative like this?
Actually, there is no result. You can perturbatively map this Hamiltonian to two local, still keeping the stochastic property.
Okay, thanks.